Okay, we're looking at UGM practice number 5. We're going to try to determine the mass of the suns using the Earth's orbit. So the F-net on the Earth, mass of the sun, mass of Earth over the radius, or the distance between the two squared. So the F-net for the Earth is just that one force, which will be 4 pi squared r over delta t squared times m. I'm using this one because I know the orbital period, because it's a year. So the mass of the sun is 4 pi squared r cubed over g delta t squared. And there's our one astronomical unit again. G times 1 year, which is 365 days per year, times 24 hours per day, times 3,600 seconds per hour, times 1 year, squared. And I get 2 times 10 to the 30th kilograms, which is a good value. Okay, so here we're doing this transfer from the Earth's orbit to Mars's orbit. This is a way you can really go. It's pretty slow. It's quicker to do a bunch of gravitational slingshots around other bodies, but this is definitely a way to do it, and it doesn't cost a whole lot of fuel. You only change your velocity twice. Once to transfer to the elliptical orbit and once to transfer to Mars's orbit. So if I'm going to transfer from the circle to this ellipse, I'm going to need to go a little faster, which is going to sort of, if you think of it like going around a curve, or if you go around the curve too fast, you slide to the outside. That's what's happening here. The gravitational force on the probe isn't big enough to keep it in the circle if it goes faster, so it goes further out. So it needs to speed up there. Now when it gets to Mars's orbit, if I look at what it's going to do if it doesn't do anything, if it doesn't change anything, it's going to do that. So I'm sort of going, I'm going to the inside. I want to go further outside. So I'm on this orbit. The gravitational force from the sun is the size of it is enough to make me do this orbit, but I really want to be in this orbit, which is further out. So I actually need to speed up again. So I need to fire my rockets backwards twice. So it pushes me, so the gases push me forward, both to transfer to the ellipse and to transfer from the ellipse to Mars's orbit. It might seem a little weird because we know that Earth's orbit, if it's orbiting with Earth, it's going faster than Mars goes. But it slows down on its trip out to Mars because it's going to the far side of the ellipse. And we want to figure out the time that it takes to travel that half ellipse. So anytime we're looking for orbital period of an ellipse, we know Kepler's third law is going to be involved. So this is the major axis of the ellipse. So this one is the radius of Earth. And this one is the radius of Mars. And so the semi-major axis is half of that. So the radius of the Earth's orbit plus the radius of Mars's orbit divided by 2. And we want to compare that to the Earth's orbit since we know stuff about the Earth's orbit. So what I know is that delta t for my elliptical orbit divided by delta t of my Earth orbit, since they're both orbiting the sun, I can compare them using Kepler's third, is radius of the Earth orbit, radius of the ellipse, which would be the semi-major axis of the ellipse, divided by the radius of the Earth orbit, which is the semi-major axis of the Earth's orbit, because it's just a circle, to the 3/2 power. So delta t for the ellipse is delta t for Earth, that is 1 year, times that ratio. And to do this, we need to figure out what Mars's orbital distance is, so we need to look that up. So I looked up that, and I figured out that it was this, which is about 1.5 times the Earth's orbital radius. And so actually, instead of having to deal with a bunch of scientific notation stuff in my calculator, I'm going to just use that information, and so I'm looking for this sum, so that's Earth's radius plus 1.52 Earth's radius over 2 over radius of Earth. So the Earth's orbital radius cancels out. And that's delta T Earth times 2.52 divided by 2. Oops, we lost our 3 halves. So that's 2.52 over 2 is 1.26. So the 3 halves power is 1.41 times delta C, the Earth, which is 1.41 years, Earth years. Oops, that's not what we wanted. That's the whole orbit. So for half the orbit, 0.707 years, which is almost exactly, by the way, the square root of 2, or square root of 2 over 2. That's just a coincidence. So it'll take 0.707 years, which is about 8.5 months for you to get to there. If you want to go on a trip to Mars this way, it'll take you 8 months to get there and 8 months to get back. So it doesn't cost a lot of fuel, but it does take a long time.